Hello, my name is Alex. I work in QuickField support team. Today we will speak about capacitance calculation with QuickField. This webinar program includes single or insulated conductor capacitance calculation. The sphere capacitance will be calculated. Then the capacitance between two conductors with opposite charge will be calculated. These are plain capacitor case, spherical and cylindrical capacitor, and the capacitance between two wires. The difference between ideal and real capacitors will be discussed. And at the end, we will study some practical cases. Transmission line capacitance and capacitance of the winding will be calculated. Now we start with capacitance definition. The capacitance is ability of conductor to store the charge in electric field. The capacitance of conductor can be calculated as the ratio of conductor's charge to the conductor's potential. Now, what is the potential? In fact, we cannot measure absolute value of potential. Only relative potential value makes sense. To calculate the relative potential value, we need to have some reference point with known potential value. Usually this reference point is a ground surface with zero potential. In case of single body, we use the infinity as a reference point. Far away from the conductor, the field fades to zero, and there we have zero potential. The total charge of the system is supposed to be zero. If our conductor has positive charge, then somewhere there is negative charge. In case of single conductor, the negative charge is moved far away, so it has no influence on the field. There is an alternative way to calculate the capacitance for the energy of electric field. In theory, both approaches give the same result. As a first example, let's calculate the capacitance of the sphere. We have an insulated sphere of conducting material. The sphere radius is 100 millimeters. The electric charge is applied to the sphere. You can see here is the analytical equation to calculate the capacitance of the sphere. Let's simulate this case in QuickField. I start QuickField and create new empty problem. The problem name will be sphere. Next, I choose the problem type. To calculate capacitance, I choose electrostatics problem type. The model class is axisymmetric. This means that there is an axis of rotation, horizontal axis of rotation, and in my model I will draw only the upper half of the sphere. Now this is the empty model, and I have to draw my sphere here. This is my sphere. This is the upper half of my sphere. The axis of rotation is a horizontal one. Now to calculate the electric field, I need to add some space around my sphere. I cannot calculate the field in infinitely large space, so this will be my calculation area. Now my model is ready, and I have to assign labels to materials. There is no electric field in the sphere, so my conducting sphere is represented by its surface. Now this is the surface of the sphere. Around the sphere there is an air. I will put a charge on my sphere at this point. And far away from my sphere the field fades to zero, so far away, usually 10 times is enough to consider that the boundary is far away. 10 times of the body's dimension. Far away from my sphere, I have the boundary. Now all objects are labeled. I have to specify physical properties for all objects. For the air, in electrostatic problem, I specify electric permittivity. Far away from my surface, from my sphere, the field fades to zero. So at the boundary, I specify zero potential. My sphere is a conductor. I don't know the potential value of this conductor, so I mark it as a floating conductor with unknown potential. And the charge. I will set some charge on my sphere. Then I need to build the mesh. I have to press one button only. Save all problem files. And I can solve the problem. The problem is solved. Let's take a look at the result. Here is the result. We can see the equilines of the electric potential. To measure capacitance, we can use the capacitance wizard. I will calculate the capacitance of my sphere. So this is the electric potential of my sphere. The charge of the sphere is here. And you can see there is an alternative way to calculate the capacitance through the energy. Let's try both approaches and compare the results. Here you can see the results on the screen. These are close values, so I believe our simulation was accurate. Let's compare the calculated value with the theory. Now here I have 11.52 and the theory gives me 11.13. There is a difference in the third digit. QuickField gives me 115 here. The difference is caused by the close location of the external boundary. The calculation area is artificially compressed. If we move the boundary further away, we will surely get better agreement with the theory. Now let's continue with the capacitance between two bodies. If we have two conductors with opposite charges, then the capacitance of this system can be calculated as a ratio of the charge, the absolute value, to the potential difference. To simulate such a system, you should apply negative and positive charge and measure the potential difference. And remember to specify the reference point with non-potential. To finish with the sphere, let's calculate the capacitance of the sphere capacitor. We have two spheres, inner sphere and outer sphere. We have positive and negative charge applied. There is some dielectric media between these spheres. And I need to calculate the capacitance of this capacitor. This simple case has analytical solution, so I will simulate the problem with QuickField and compare the results with the theory. Let's start QuickField and simulate. Now this is my simulation problem of spherical capacitor. The problem type is electrostatics. The model class is axisymmetric. The axis of rotation is a horizontal one. There is a dielectric media between spheres. I put negative charge on the outer sphere and positive charge at the inner sphere. The sphere is a floating conductor with unknown potential. And I decide to put the reference point at the outer sphere. I can choose any point, so I have chosen the outer sphere as a reference point. I set 0 potential at the outer sphere. Now let's take a look at the result. Again, you can see the field lines, the equipotential lines. I can adjust the field picture and switch on the color map of different values. And I can switch on the vectors. Such a nice picture we get. I can calculate electric field values in different points. In this point and here. And I can build contours to make XY plot. So I build the contour here from outer sphere to inner sphere. And now let's take a look at the XY plot. Here we can see the electric strength distribution. And the same I can see in the table. And I can select values and copy all the data. And with contours, I can calculate integral values. To calculate capacitance, I need to divide the charge by the potential difference. The charge, I know. Here is the value. Now, what is the potential difference between these spheres? QuickField has such an integral value. So this is my contour. And I calculate the potential difference. Now let's calculate the capacitance in this system. I know the charge. It's 1000 picocoulombs. I divide the charge by the potential difference. And what I get? 22.253. Let's compare with the theoretical solution. 22.253, 22.253. These are the same values. In this example, our model is fully agreed with physical reality. We didn't restrict the calculation area, so we get accurate result.